Yesterday we did a demonstration where we showed you what a standing wave looked like. We sent a wave down through a string from one end to the other, reflected off of that end, came back, interfered with the wave that was still going down, and produced a wave that looked like it was standing still. That's what a standing wave is, a wave that appears to be standing still. Now, it isn't really, because in reality, there's a wave going down and a wave coming back. So how does it appear to be standing still? Well, it's because what we're looking at, the wave that appears to be standing still, is really an interference pattern. It's the interference of the wave that's traveling down toward the barrier and the wave that's reflected off of the barrier coming back. We could determine using the superposition principle that we learned yesterday and the day before what that interference pattern would look like, but we know that at very specific frequencies, it will look like the wave is standing still. We call those frequencies at which this wave appears to be standing still, the 5 hertz, the 10 hertz, the 15 hertz, like we saw in yesterday's demonstration. We call them resonant frequencies. The first frequency, 5 hertz, was the resonant frequency. The second one that occurred at yesterday, 10 hertz, was the first overtone. Now, when we saw this yesterday, when we looked at this yesterday, it looked more or less like this. You saw two fixed ends. The string was attached at one end, the string was attached at the other end, and then we had a string that appeared to be here and here all at the same time. Of course it wasn't. The string was going back and forth between the blue spot and the green spot at all times, but it looked like the string was in all of those places at the same time. Where it didn't actually move was these spots in the middle, these spots right here. These blue and green areas are where we had constructive interference. The wave going down interferes with the wave coming back and constructively to produce bigger crests and bigger troughs. We call that an antinode. An antinode is a result of constructive interference. You also saw those points yesterday where the wave wasn't moving. The string wasn't moving at all. That's what we call a node. Antinode versus node. And where we had the nodes were areas of destructive interference. The whole thing looked like it was standing still. In reality, it was only the node that was still. The antinode wasn't. The string was going up and down, but it looked like it was standing still because it was going up and down so many times per second. Destructive interference for the nodes, where it was standing still. Constructive interference for the antinodes, where it just looked like it was standing still. Now we're going to figure out here when those standing waves occur, at what frequencies they occur. We saw experimentally yesterday they occurred at 5, 10, 15, 20 hertz, but those frequencies, those resonant frequencies of the string can change easily. If we made the string tighter or looser, the resonant frequency would change, maybe from 5, 10, 15, 20 to 8, 16, 24, and 32. If we change the length of the string, the resonant frequency would change as well. If we change the density of the string, the resonant frequency would change as well. How do we determine at what frequencies or predict at what frequencies that will occur? Let's draw the standing waves. The vertical lines we see here represent the ends of a string that's fixed at both ends. So we're going to draw the first harmonic, what we call the first harmonic, which is the first standing wave that we would see, then the second, then the third, and so on, and derive some equations to figure out what frequencies they would actually occur at. The first standing wave that we would see would look like this, with one antinode and two nodes, right? A node at both ends and an antinode in the middle. Yesterday I showed you the second one, not the first one, because it would have been difficult to see the first one with the demonstration that we did. Okay, but had I showed you the first one and had it worked the way that it's supposed to work, then this is what you would have seen. The second one, as you did see yesterday, looked like this, where we had two antinodes and how many nodes? Three nodes, right. Two antinodes and three nodes. The next one that we would have saw, the next one that we did see yesterday, looked like this. This one we had, well, we went from 1 antinode to 2 antinode to 3 antinodes. We went from 2 nodes to 3 nodes to 4 nodes. 1, 2, 3, 4. You can keep going. We don't need to keep going, so we'll stop it there, okay? Now, I wanted to find the length of this string. The length of this string is L, from one end, from one fixed end to the other. Yesterday, it would have been from that mechanical wave producer that we had to the leg of the desk that we had the string tied to. That would be the length of the string, L. And that's the case for all 3 of these diagrams. The next thing that I want to do is define the length. This is an important step here. Define the length in terms of the wavelength. Let's draw over here just a little reference picture. Okay, this is how much of a wave. If I go from here to here, in other words, from here to here, how much of a wave is that? That's a half a wave. Good. So L is going to be 1/2 of lambda. Does that make sense? Half of lambda, half of a wave. So we're going to just rearrange that and solve for lambda. We get 2 times L. Now let's do it for the next one here. Okay, I'm going from here to here. How much of a wave is that? Going from here to here, right? How much of a wave is that? That's a wave. That's a full wave, right? So we're going to say L is equal to lambda for that one. Really, I don't need to rearrange this one because I've already solved for lambda, but I'm just going to change the order of it just for symmetry there. Lambda is equal to L. What about the next one here? How much of a wave is this? There's 1, and then we go to there. That's like this one, right? Go right here to here. How much of a wave is that? That's 1.5. Now I'm going to break that as a fraction. You don't have to write it as a fraction. You could write it as a decimal easily, but I'm going to write it as a fraction because it helps us to see a pattern that should pop up in just a moment here. So I'm going to say L is equal to 3/2 or 1.5 lambda. Lambda, therefore, if we rearrange that, the 2 goes up, the 3 goes down. Lambda is equal to 2/3 L. Again, it's not critical that we use the decimal, or sorry, the fraction, but it does help us to see a pattern that should emerge in just a moment. So, draw your diagram. Get L in terms of lambda, and then rearrange to solve for lambda. Then use the wave equation. Remember the wave equation? V is equal to F times lambda. Rearrange that to solve for F. F is equal to V over lambda. Now let's sub in lambda for lambda. So it becomes F is equal to V over what? 2L. The frequency of the first harmonic, the frequency of the first resonant frequency would be the speed of the wave divided by 2 times the length of the string. For the next one, we would say F is equal to V over lambda. What's lambda equal to? What's lambda? L. So it becomes F is equal to V over L. The next one that we would see, the second one that we saw yesterday was at 10 hertz, 5 hertz, then 10 hertz. The first one was V over 2L. The second one was V over L. The third one that we saw yesterday was 15 hertz, V over lambda. V over lambda is 2/3 L. We could leave it like that if we wanted to. It's kind of ugly. So I'm going to just simplify that a little bit. V over 2/3 L is exactly the same thing as saying V 3V over 2L. Right, we're dividing by a fraction, 2/3. If we multiply by the reciprocal of that, 3 over 2, then we get 3V over 2L. Now what I want you to notice here is the pattern. The first one we call our first harmonic. The first harmonic. Notice the value of the second one. The second one, F2, is twice the value of F1. Right? If you take F1, multiply it by 2, then you get V over L. Right? Multiply by 2, you get 2V over 2L, which is the same as saying V over L. If you take the first one and multiply it by 3, you get 3V over 2L. In other words, you get the third harmonic. Yesterday, the first harmonic occurred at 5 hertz. When did the second one occur at? Twice the first one, at 10 hertz. When did the third one occur at? 15 hertz. 3 times the first harmonic. Does that make sense? Okay, that second harmonic we could also call the first overtone, and this third harmonic we could also call the second overtone, because it's the second one after, the second one over the first harmonic. Now take a look at that first harmonic again, V over 2L. When you pluck a guitar string, anybody play the guitar here? Nobody plays the guitar? Jacob does. Jacob plays it very well, actually. You pluck a guitar string and you hear a sound, right? That corresponds to a resonant frequency of that string. When you pluck the string, there's all kinds of frequencies set up there. Most of them don't last. Most of them die out right away, except the ones that correspond to the resonant frequencies. So what you're hearing when you pluck a guitar string is a standing wave set up in that string. Does that make sense? Now, how do you change the pitch of that note? How do you change the sound that you hear when you pluck a guitar string? There's a couple ways. What's one way? You shorten the string, and how do you do that? Put your finger on a fret. When you put your finger on a fret, now all of a sudden you're making the string shorter than it was before. You pluck the string. That changes the resonant frequency of the string, so that changes the standing wave that will be set up when you pluck it, and that changes the sound that you will hear, right? In fact, you guys know that if you put your finger on a fret, what you're doing is effectively shortening the string. As L becomes smaller, F becomes bigger. It should, right? Mathematically, as L becomes smaller, F becomes bigger. And you know from experience, when you pluck a guitar string with the finger on a fret, the pitch gets higher, right? What's the other way to change the pitch of a string, of a guitar string? Besides putting your finger on a fret. You can stretch it, right? You can tighten it with a tuner, right? When you tune it, what you're really doing is loosening it or stretching it. And when you loosen it or stretching it, you're changing the speed of the wave in that string. So this time V becomes higher. As V becomes higher, F becomes higher. So when you turn the tuner to tighten the string, what you're really doing with a tighter string is making the speed of the wave in the string faster. And as the speed is bigger, then the frequency is bigger. That's why when you pluck the string when it's tight, it sounds like a higher pitch than when it's not tight. You're creating a higher resonant frequency, a higher first harmonic standing wave, and therefore a higher pitch sound that you hear. Does that make sense, guys? All right. Now, we've gone through all these derivations, 3 of these derivations. We could go through 4, 5, 6 derivations. But I'm going to tell you this. The reality of it is that you only really need to be able to do the first one. Because if you need the second harmonic, all you got to be able to do is multiply the first harmonic by 2. Or if you need the fifth harmonic, you need to be able to multiply the first one by 5. Or if you need the 17th harmonic, you need to be able to multiply the first one by 17. So really, if you can do the first harmonic, you're good with the rest of them without bothering to derive the equations for the rest of them. The reason we did derive a couple more was just to show you mathematically that the second harmonic is twice the first harmonic and the third one is 3 times the first harmonic. You don't really need to be able to derive those or use those equations. Make sense? Okay, we're going to do a question on that in just a second, okay? When we do, I want you to remember this. When we do any question involving standing waves, I want you to remember this. If you're not going to derive the rest of the equations, second harmonic, third harmonic, 17th harmonic, then you always need to remember to go through the first harmonic. So if you want to find the third, get the first and multiply it by 3. If you've got the third, what should you do? Divide by 3 to get the first, and then do your thing, right? So go through the first. Either get the first and then multiply it by something, or if you've got something else, the 17th, then divide by 17 to get the first, and then use your equation. So always work through that first harmonic. Let's take a look at this example that's not in your textbook this time, so unfortunately you're going to have to copy this one out. So the question says a 25 centimeter long string, centimeter, right? Draw attention to that, is set into vibration. The speed of the wave, through the string is 500 meters per second. What are the first 3 possibilities for harmonics in the strings? In other words, what are the first 3 resonant frequencies that we would see in this string? Or if it was a musical instrument, what are the first 3 harmonics that we would hear in the string? By the way, when you pluck the guitar string, there may be 2 or 3 or 4 harmonics. You hear them all kind of combined. Okay, and that refers to the quality of the sound. Okay, quality music, like defined musically, is not like, oh, this is a beautiful sound, it's great quality. The quality of the sound is defined as the number of harmonics that you end up hearing. So the quality of the sound would be, I hear the first 2 harmonics, or I hear the first 3 harmonics combined, or whatever. So let's do this here. I'm going to draw the picture, and I'm going to derive the equation every time. The reason I'm going to do that is because these equations are not on your data sheet. So the more we derive them, the more familiar with them we become. Just like that satellite equation where FC was equal to FG, we derived it every time we did a question so that when you worked on a test question, it was more familiar to you, right? You should do the same thing. Derive it each time so that it becomes old hat come test day. Here's the first harmonic. Here's the first harmonic. This was L. We know that L was equal to how much of a wave? Half of a wave, right. So lambda would therefore be equal to 2 times L. Then we said V is equal to F times lambda, or F is equal to V over lambda, or F is equal to V over 2L. There's my equation for the first harmonic. Now, we could derive the equation for the second and the third as well, right? Do we need to? Once we get the first, what do we got to do? Just multiply it, good. Just multiply it by 2 and 3. So let's get that first harmonic. Let's get F1. F1 is equal to V, which is 500 meters per second, divided by 2 times the length of the string, which is 0.25, bless you, meters. So 500 divided by 0.5 gives me a frequency of 1,000, I think, isn't it? Which we would technically round to 1.0 times 10 to the 3 hertz. There's the first harmonic. There's the first sound that we would hear. Now, you could absolutely, if you wanted to, derive the equation for the second one and for the third one. But the easier way to do it is just to say the second one, F2, is equal to 2 times F1. Or 2.0 times 10 to the 3 hertz. And the third harmonic is 3 times F1, which is 3.0 times 10 to the 3 hertz. Go through the first harmonic. If you want to find a harmonic, calculate the first and then multiply it by whatever. If you had the value of the third harmonic already as 3,000 hertz, then divide it by 3 to get the first harmonic, and then do the equation. Always, my recommendation at least, is always do the equation with the first harmonic. Then multiply it by something, or divide it by something to get the first harmonic, and then do the equation. Does that make sense?